The last two examples in this section ask us to test for convergence or divergence of the series and identify the test used. So this is looking at all the things that we've learned from section 9.2 until now. First, you identify what you're looking at. If it's an alternating series, we handle it like we did for examples 1 through 5. If it's not an alternating series, we think of how we looked at problems in section 9.2, 9.3, 9.4. So let's go ahead and look at these two examples and determine if they converge or diverge. Number 6 is the sum from n equal 1 to infinity of 1 over n times the square root of n plus 1. Well, this is not an alternating series because I don't have a negative 1 raised to the n or a negative 1 raised to the n plus 1. So I'm going to handle it like I did in sections 9.2, 9.3, and 9.4. What do I do first? I figure out if it's a known series. It is not a known series, so then I have to find a different test to determine if it converges or diverges. Typically I try the nth term test, but the problem is that the limit as n goes to infinity of 1 over n times the square root of n plus 1 is equal to 0, so this test fails. Now the nth term test does fail often, but when it doesn't fail, it allows us to determine if a series diverges very quickly. Since the nth term test failed, we now get to choose integral test, direct comparison, or limit comparison. I typically try direct or limit, and for both of those you have to determine what you're comparing it to. So let's go ahead and figure out what we would compare this to. What is the leading term of the numerator? 1. What is the leading term of the denominator? Well, it would be an n times the square root of n, which is really just 1 over n times n to the 1/2, or you can think of that as 1 over n to the 3/2. So we're going to compare it to the p series, the sum from n equal 1 to infinity of 1 over n to the 3/2. Again, that's a p series. P is equal to 3/2, which is a number greater than 1, therefore we know that this would converge. Let's go ahead and try the limit comparison test. The limit comparison test says to take the limit as n goes to infinity of given. Your given is this guy, 1 over n times the square root of n plus 1, divided by the known, or times the reciprocal of the known. And the known is this guy right here, but since this has a radical in it, the given, let's go ahead and just use the radical form. And so the reciprocal of the radical form would be n square roots of n over 1. We notice right away that our n's will cancel, and then we're left with the limit as n goes to infinity of the square root of n over the square root of n plus 1. Well, we know that that is infinity over infinity. And we could use L'Hopital's rule, but these are just powers of n, so it's really just the square root of n over the square root of n if we're looking at those leading terms. And we know that the square root of n over the square root of n reduces to 1, so we're looking at the limit as n goes to infinity of 1, which is equal to 1. Well, 1 is a finite positive number. Therefore, by the limit comparison test, our series converges. And here we're not stating that it converges absolutely because we didn't take the absolute value of a sub n to determine if this series converged or diverged. Last one, number 7. The sum from n equal 1 to infinity of 1 over the natural log of n plus 1. Well, this is not alternating because I don't have a negative 1 to the n or negative 1 to the n plus 1. It is not a known series, so the first thing I always try is the nth term test. But the problem is that the limit as n goes to infinity of 1 over the natural log of n plus 1 is going to give me 1 over infinity, which is 0, which means that my test fails. Now I have to determine if I want to use the integral test, direct comparison, or limit comparison test. Well, you would not be able to integrate this, so we'd actually have to use a comparison to do this. But this is strange because of that natural log. If the natural log wasn't there, then you would probably look at this and say, I'm going to compare this to a p series because this looks like a p series. Even with the natural log there, it does look like a p series. Now think about a p series. You know, for a p series, which is 1 over n to the p, if p is less than or equal to 1, you diverge. And if p is greater than 1, you converge. Well, the natural log of n fits into this category. It makes it where that power is a power that's less than 1, because the natural log of n grows slower than n to the first power. Therefore, if you're comparing it to a p-series, you need a p-series that diverges. Since we know that we think it's going to diverge, we're going to compare this to that p-series, the sum from n equal 1 to infinity of 1 over n. We're looking at that p-series, p is equal to 1, therefore we know we are going to diverge. If we were to try the limit comparison test, if we take the limit as n goes to infinity of given 1 over the natural log of n plus 1 times the reciprocal of the known n over 1, the problem with this is that this test is going to fail. Well, the limit as n goes to infinity of n over the natural log of n plus 1 is currently infinity over infinity. Since we have that natural log there, let's go ahead and use L'Hopital's rule. So we're looking at the limit as n goes to infinity of the derivative of n is 1. The derivative of the natural log of n plus 1 is going to be the derivative of n plus 1, which is 1, over itself n plus 1. Well, if we're dividing by a fraction, we know it's the same as multiplying by its reciprocal. So we're just looking at the limit as n goes to infinity of 1 times n plus 1, which is equal to infinity. This is not a finite positive number. So my test fails. So I cannot use a limit comparison test here because I don't end up with a finite positive number. Let's try the direct comparison test instead. Since we know that this is going to diverge, this has to be the smaller series. That makes this guy here my a sub n, and the given my b sub n. So we know we have 0 less than a sub n less than or equal to b sub n. The a sub n is my 1 over n. Is that less than or equal to the b sub n is my given 1 over the natural log of n plus 1? Well, let's say I'm not sure here. We can always cross multiply. So if we cross multiply, we have the natural log of n plus 1. Is that less than or equal to n? I'm not sure because of the natural log. Let's get rid of the natural log. How do we do that? We make e the base. So e raised to the natural log of n plus 1. Is that less than or equal to e raised to the n? Here these cancel and I have n plus 1 less than or equal to e to the n. Is this true? Well, this here is an exponential function, and this here is a polynomial. Exponential functions are larger than polynomials. If we're unsure, let's just plug in a few numbers just to show that this is true. Well, when n is equal to 1, we'd have 2 less than or equal to e, which is approximately 2.71. Is 2 less than or equal to 2.71? Yes. When n is equal to 2, we'd have 3. Is that less than or equal to e squared? Yes, because e squared is 7.4. When n is equal to 3, does this still hold true? Well, is 4 less than or equal to e cubed? Yes, because again, it's an exponential and e cubed is 20.1. Therefore, this is true. And since that's true, we know that by the direct comparison test, our series diverges. Why does it diverge? Because the one that we were comparing it to diverged. We don't try the alternating series test on this series because it's not alternating. You can only use the alternating series test on a series that alternates. That's it for alternating series.